Imagine gazing at this first real photograph of a black hole, that iconic fiery ring from 2019, shimmering across your screen. Now imagine what happens when our vision gets sharper, more dynamic, when black holes, once mere shadows in the void, suddenly burst into vibrant color. What if the universe's darkest secrets were about to be revealed not in blurry black and white, but in exquisite, high-definition living color? What new realities could we uncover? Could the very rules of physics as we know them be rewritten? For centuries, black holes have been the ultimate enigma, so massive that not even light escapes, invisible to our eyes and cameras alike. They're cosmic powerhouses, warping space and time, serving as the backdrop for science fiction and the obsessions of physicists around the globe. The mysteries swirling at the edge of these monsters have always seemed just out of reach. But what if that was about to change? Thanks to a breathtaking leap in technology and technique, astronomers are on the cusp of transforming how we see and understand black holes forever. We're about to move from flat snapshots to multidimensional technicolor revelations. The Event Horizon Telescope, EHT, has spent years pointing humanity's eye at the universe's most extreme objects, and now it's pioneering a revolution that could shatter decades of astrophysical dogma. How did we get here? The journey isn't just about technology. It's a story of global cooperation, wild ambition, and the relentless drive to answer questions that have haunted us since Einstein first sketched his equations. To appreciate just how monumental this shift is, let's rewind and build the foundation of our cosmic quest. The Event Horizon Telescope is not one telescope. It's a planet-sized array, weaving together signals from massive radio observatories scattered across 6 continents. This mega-network uses a technique called Very Long Baseline Interferometry, or VLBI, a tongue twister that basically means turning Earth itself into a gigantic lens. By synchronizing these distant dishes, scientists can simulate a scope as wide as our world, capturing details far too small for any single telescope to see. But there's a catch. Light doesn't always travel freely through the universe. Black holes are veiled by swirling shrouds of gas and dust, obscuring them from traditional visible light telescopes. That's why the EHT focuses on radio waves, specifically the short millimeter and sub-millimeter wavelengths that can slip through the cosmic fog and reach us mostly intact. Here's where things get both technical and thrilling. The EHT's birth traces back to a blend of theory and relentless innovation. In 2017, its fledgling global network took aim at 2 cosmic giants, Sagittarius A, the supermassive black hole anchoring our own Milky Way, and M87, an even bigger beast residing in a distant galaxy. After painstaking years of data analysis, in April 2019, the world met M87, a glowing orange ring surrounding a dark central shadow. That image wasn't just a scientific milestone, it was a cultural phenomenon, splashing across front pages, igniting imaginations, and proving Einstein right in one of the universe's most extreme environments. As Heino Falke of Radboud University put it, this shadow, caused by the gravitational bending and capture of light by the event horizon, reveals a lot about the nature of these fascinating objects, providing a direct test of general relativity in the strong field regime. Soon after, the EHT achieved another monumental feat, the 2022 unveiling of Sagittarius A, our home galaxy's own black hole. Both images confirmed predictions and, in the words of Paul T.P. Ho of the East Asian Observatory, many of the features of the observed image match our theoretical understanding surprisingly well, bolstering our confidence in the interpretation of our observations and the accuracy of our mass estimations. But those images, for all their historical significance, were essentially black and white, maps of radio intensity stitched together from a single frequency band each. They showed us shapes and shadows, hints of swirling motion, but little about what was truly happening at the edge of the abyss. Here's the crux. To unlock the secret lives of black holes, their turbulent jets, their swirling magnetic fields, and the dance of matter plunging into the void, we need more than just monochrome snapshots. We need to see in color. Color, in the universe's language, is frequency. Human eyes interpret color based on wavelengths of light, but our eyes are blind to the radio frequencies where black holes broadcast their stories. Instead, radio telescopes see colors as different bands of radio frequency. By observing the sky at multiple bands, astronomers can synthesize a color image, each hue revealing different physical processes, from the energy of particles to the structure of magnetic fields. But until now, creating these color radio images has been a monumental challenge. Most radio telescopes can only look at one frequency at a time. To build up a color picture, astronomers had to observe the same black hole multiple times at different frequencies, then hope nothing had changed in between. For slow, stable objects, that works. But black holes are anything but stable. They devour matter, spew out jets, and swirl with magnetic chaos on timescales of minutes or even seconds. Imagine trying to capture an action shot at a soccer match, but your camera takes each color channel, red, green, and blue, separately, with a delay between each shot. The resulting image would be a blurry, misaligned mess. Now scale that up to a swirling vortex of hot gas orbiting a supermassive black hole, thousands of light years away, and you start to see the challenge faced by astronomers. So what changed? Enter the latest breakthrough, frequency phase transfer, or FPT, a technique that could be the game changer we've been waiting for. Let's break it down. Earth's atmosphere is a blessing and a curse for astronomy. While it protects us from harmful cosmic radiation, it wreaks havoc on high-frequency radio waves, smearing and distorting the signals that astronomers desperately need to resolve fine details. Optical astronomers get around this by using adaptive optics, laser systems that twinkle with the movement of the atmosphere, helping to correct images in real time. But for radio telescopes, especially at the highest frequencies, the challenge is even tougher. The EHT team's scientists, inspired by these methods, devised frequency phase transfer to tackle the distortion problem head-on. By simultaneously observing at two different frequencies, say 3 mm and 1 mm wavelengths, the team can use the more stable, longer wavelength data to calibrate or correct the atmospheric effects on the shorter wavelength data. This is like using a slow, steady heartbeat to anchor a racing pulse, giving clarity to the most turbulent signals. And it works. In a recent study led by Sarah Isaoun and colleagues, the technique was demonstrated for the first time on an Earth-sized baseline. Multiple radio observatories captured the sky at two frequencies, with the 3 mm data compensating for the distortions in the 1 mm signal. The result? Sharper, more detailed images, and, most importantly, the ability to capture multiple frequencies in rapid succession. For the first time, astronomers can build up color radio images of black holes, unlocking layers of information hidden in their electromagnetic rainbows. Expert Michael Johnson from the Center for Astrophysics summed up the excitement. Multi-frequency imaging, combined with advanced algorithms, unlocks unprecedented insights into black hole physics, allowing us to probe the fundamental nature of space-time and gravity. But the innovations don't stop there. The EHT collaboration is already working on its next iteration, the Next Generation EHT, or NGEHT. More telescopes across the globe, double the bandwidth, even higher frequencies, reaching up to 345 GHz. These upgrades promise to make our images not just sharper, but alive, with enough detail to reveal dynamic changes, to watch black holes evolve in almost real time. At this new frontier, cutting-edge algorithms also play a starring role. The Primo algorithm, for instance, reconstructs sharper images from the sparse, noisy data the EHT collects. With multi-frequency data and advanced computational power, astronomers can now peer deeper into the maelstrom, mapping magnetic fields, measuring the energy of jets, and even, as Kazunori Akiyama of MIT imagines, creating movies of black holes, observing how they evolve over time and interact with their surroundings. All this progress isn't just about prettier pictures. Each new layer of data sharpens our understanding of some of the universe's most fundamental mysteries. How do black holes grow and launch powerful jets of energy? How do magnetic fields shape their environments? Could we spot the signature of new physics, anomalies in the event horizon's shadow, or evidence of exotic matter? As Alexander Raymond of NASA's JPL speculates, at 345 GHz our images will be sharper and more detailed, which in turn will likely reveal new properties, potentially challenging existing models of black hole accretion and jet formation. Yet, as we sprint toward this technicolor future, colossal challenges and even bigger questions loom on the horizon. Can we really trust these new, algorithm-driven portraits? What if our assumptions about black holes are fundamentally flawed? Could this flood of color data finally force us to rewrite the laws of gravity? Or might it unmask new, even stranger cosmic phenomena? And, perhaps most tantalizingly, what will we see when, for the very first time, we watch a black hole live in color as it bends space-time and devours the universe around it? The answers may shake the very foundation of astrophysics. But first, let's delve deeper into the challenges, controversies, and mind-bending implications of this technological leap. Because the next chapter in the black hole saga is being written right now, and it promises to be unlike anything we have ever witnessed. But as the curtain rises on this new era of technicolor black hole observation, the universe greets us with profound intrigue and a touch of uncertainty. The first color images from the Event Horizon Telescope and its successors will not just be prettier pictures, they will be data-dense, multi-dimensional windows into phenomena we've barely begun to understand. And with each step forward, we must grapple with not just excitement, but the limits of our own knowledge. The path ahead is both exhilarating and unpredictable. Let's start with the upside, the doors that these new techniques are about to open. For the first time, astronomers won't be peering at a blurry orange donut, but rather a living, moving, color-coded story. By capturing radio light at many frequencies simultaneously, scientists can finally track how the complicated mess of hot gas, magnetic fields, and gravity dance together at the very edge of space and time. According to Dr. Shepard Dolman of the Center for Astrophysics, this new color vision allows us to tease apart the effects of Einstein's gravity from the hot gas and magnetic fields, offering a more complete picture of black hole environments. That means sharper boundaries between what's governed by physics we already know, like general relativity, and the messy, energetic behavior of matter swirling around the event horizon. It means a clearer test of where the known meets the unknown. But what exactly do these advances promise? Imagine, instead of a still image, we could see something like a time-lapse movie of a black hole's accretion disk, watching gas spiral in and jets burst out frame by frame in different colors representing different energies. This could finally let scientists answer long-standing questions, like how are black hole jets launched? Why do some black holes grow quietly while others become cosmic particle cannons? And what exactly happens at the event horizon, that shadowy boundary where light and information seemingly disappear? In practical terms, the Next Generation Event Horizon Telescope, or NGEHT, is set to add new observatories, double its bandwidth, and push into even higher frequencies, up to 345 GHz. This leap will sharpen images, boost sensitivity, and allow astronomers to dive deeper into the maelstrom of physics near a black hole. Alongside this hardware, there are software revolutions underway. The Primo algorithm, for example, is helping transform incomplete, noisy data into crisp, detailed images. Michael Johnson at the Harvard-Smithsonian Center for Astrophysics puts it simply: multi-frequency imaging, combined with advanced algorithms, unlocks unprecedented insights into black hole physics, allowing us to probe the fundamental nature of space-time and gravity. This is more than a new lens, it's a new sense altogether. It's as if, after centuries of hearing the universe in black and white, we're about to listen in full orchestra, with every instrument clear and distinct. But new tools bring new risks and controversies. And this is where the scientific adventure sharpens into real drama. Can we fully trust these dazzling, reconstructed images? How do we know they aren't just artifacts of the algorithms or wishful thinking on the part of excited astronomers? Some critics have already raised their eyebrows at the interpretation of EHT's first black hole images. Because the data from so many telescopes is combined and reconstructed with heavy computational lifting, it's possible for biases or errors to creep in. What if the colorful details we see aren't truly features of the black hole, but ghosts of the method used to assemble the data? This is not just a theoretical concern. The very first image of Sagittarius A, the black hole at the center of our own galaxy, was so tricky to assemble that about 80% of the raw data had to be discarded due to weather and technical issues. Algorithms did the rest. As one astronomer quipped, "We're not just photographing black holes, we're interrogating them, pixel by pixel, with the best lie detectors we can build." To guard against illusion and error, scientists cross-validate their images using different algorithms, synthetic data, and by comparing observations of known, well-modeled targets, like bright quasars. But as we push toward higher resolutions and more complex reconstructions, the line between measurement and imagination can blur. This challenge, balancing innovation with skepticism, sits at the heart of the coming black hole revolution. And what if, as resolution and color fidelity sharpen, we turn up anomalies, features that do not fit any current theory? Imagine uncovering structures near the event horizon that violate general relativity, or discovering unexpected periodic signals hinting at new forms of matter, or even tiny black holes orbiting the main monster. The possibility of paradigm-shifting discoveries is real. Heino Falke, one of the theoretical architects behind black hole imaging, said, "The shadow caused by the gravitational bending and capture of light by the event horizon reveals a lot about the nature of these fascinating objects, providing a direct test of general relativity in the strong field regime. But if future images do not match the predictions, if the shadow looks wrong, or if jets and disks behave in ways our models cannot explain, then it could mean new physics is lurking in the dark." This is where risk and reward collide. On one hand, multicolor imaging and time-lapse observations could finally provide the evidence to confirm or disprove Einstein's greatest predictions. On the other, they could confront us with mysteries that force a rewriting of the textbooks. The implications ripple far beyond astrophysics. Black holes are the ultimate cosmic laboratories for gravity, quantum information, and the behavior of matter at its extremes. If we see hints of physics that don't fit, it might help unify the two great pillars of 20th century science, general relativity and quantum mechanics, a quest that has haunted physicists for generations. So, what practical lessons and benefits can viewers like you take from this rapidly evolving story? It's easy to see astrophysics as a field of distant, abstract beauty, but the lessons from multicolor black hole imaging penetrate into the heart of how we do science, and how we think about truth, uncertainty, and discovery. First, these advances remind us that no scientific image or result is ever final. Our best ideas and pictures are always limited by the tools and methods we use. The world's top astronomers did not stop at the first black and white EHT photo. They immediately asked, how can we see more? How can we be sure what we're seeing is real? In a world swirling with information, images, and news, much of it processed by algorithms, the same lesson holds for all of us. Always ask, what are the limits of this method? How could it fool me? What am I not seeing? Second, the pioneering teamwork behind the Event Horizon Telescope is a powerful lesson in global cooperation. Dozens of telescopes in far-flung deserts and mountaintops, thousands of scientists from rival institutions, all united by the common pursuit of knowledge. Their breakthroughs come not just from blazing individual genius, but from collective effort and relentless cross-checking. When we face seemingly impossible problems, be it in science, health, or climate, maybe the EHT can be our model. Third, the story of technicolor black holes is a testament to the value of curiosity-driven research. Few people outside astrophysics predicted the world would one day see the unseeable, a black hole's shadow. Yet thanks to decades of steady investment in obscure technology and patient, meticulous science, we now find ourselves on the threshold of a new cosmic vision. It's a reminder that pursuing answers to today's wildest questions can lead to tomorrow's world-changing breakthroughs. And for those hungry for personal inspiration, consider this. Every time we sharpen our cosmic eyesight, we deepen our understanding of our own place in the universe. Black holes are not simply distant monsters. They are anchors for entire galaxies, engines that shape the formation of worlds and even life itself. To gaze at their true colors is, in some small way, to glimpse the forces that made us possible. So, circling back to our key question, can we fully trust this new generation of black hole images and the methods behind them? The honest answer is, we can trust them, but only provisionally and with humble skepticism. Science is not the search for certainty, but the continuous expansion of what is knowable. Each new color-rich image is the best answer we have yet, but never the last answer. Each advance brings us closer not just to understanding black holes, but to understanding how we understand. As for the unexpected discoveries these technicolor horizons may reveal, we should be prepared for surprises. Some might rewrite the laws of physics. Others might simply paint a more beautiful and intricate universe than we ever imagined. And here's a secret fact. The NGHT's leap in resolution is so dramatic that for the first time we might catch tiny black holes, orbits, and snapshots of matter literally plunging through the point of no return, the event horizon itself. If so, those first technicolor time lapses could hold the universe's most elusive secrets, frame by frame. In the end, the adventure of black hole imaging is a shared journey. Every image, every pixel, is a bridge from our tiny planet to the distant, mysterious heart of the cosmos. The universe is ready for its close-up. Are you? If you enjoyed this deep dive into the cutting edge of astronomy, make sure to like, subscribe, and share your thoughts in the comments. What mysteries do you hope we uncover in the next generation of black hole images? And, if you could look at any object in the universe